Hello, guys. Hope you are doing well. Today, we are going to talk about gas laws. So we're going to start talking about our final unit of chemistry, which is gases. And in gases, what we're really looking at is how temperature, pressure, volume, and amount of moles actually really affect the properties of gases. So today what we're going to do is we're just going to kind of get into the basics of that and talk a little bit about temperature and pressure, behavior of gases, and then just some gas properties. All right. So we're going to start and jump in to temperature. Okay, guys, you guys should know what temperature is. All right. And in chemistry, most of the time we use Celsius. However, anytime we are doing gases, we actually use a different temperature called Kelvin. All right. And gases always, like if we're talking about gases, you always need to convert the temperature into Kelvin. All right. Luckily, converting from Kelvin to Celsius or Celsius back to Kelvin is really, really easy. And bonus, we don't need to know how to convert from Fahrenheit. We don't even measure in Fahrenheit, so it's not an issue. So you don't need to know how to do that. Okay, so if I want to go from Celsius to Kelvin, all I have to do is add 273. So you take your degree Celsius, add 273 to it, and that gives you your Kelvin temperature. Then, if you want to go from Kelvin back to Celsius, you just subtract 273. Super easy. And it's on the periodic table, so you don't even have to remember the number. So it's pretty simple. So just add or subtract 273. All right, so let's do this first one. All right, if I have negative 167 degrees Celsius and I want that to be Kelvin, just take negative 167, add 273 to it, plug it into your calculator. When I did that, I got 106 Kelvin. That's it. It's pretty simple. All right, guys, we're going to do all of them because it shouldn't take us very long to do these. All right, they're easy. All right, so if I have 1,100 degrees Celsius and I want to get to Kelvin, once again, I'm just going to take my temperature in Celsius and add 273 to it. And that should give me, again, add it together, and you get your Kelvin temperature. So I got 1,373 Kelvin. All right. Now, this time, we are going to convert from 321 Kelvin into Celsius. So Kelvin to Celsius, we're just going to subtract 273 now. So 321 Kelvin minus 273 gives us 48 degrees Celsius. So yeah, it's pretty simple. All right, now the next question is like a little bit more tricky, but it's not bad. Okay, so it says, how does the temperature change in Celsius if it changes from 20 degrees Celsius to 255 Kelvin? Okay, guys, so the first thing we would need to do here is we would need to convert both of these to the same, basically to the same unit. So since we have one in Kelvin and one in Celsius, we need to convert one of them. All right, since we want to know the temperature change in Celsius, it's going to be easiest to probably convert to Celsius. So I'm going to take this 255 Kelvin, subtract 273 from it, which when I get that, I get negative 18 degrees Celsius. And then you're just wanting to know how much the temperature changes. So we went from 20 to negative 18. So that is that our temperature decreased by 38 degrees. And boom. That's how you convert to Kelvin. So anytime you see a gas law problem, if your temperature is given to you in Celsius, you always need to convert it. We can never leave our temperature in Celsius. If you do, you will get the answer wrong. So always convert to Kelvin every single time. Okay? All right, now then the next variable we haven't really talked about very much this year is pressure. I'm not going to specifically define volume and moles today because we've talked about those a lot this year, but I will define pressure for you guys. Okay, so pressure is defined as the number of collisions and the force of the collisions of the atoms on the walls of the container. Right, so the equation for pressure is force divided by area. All right, so basically in gases, we are looking for how many gas particles are hitting the walls of my container and like how hard are they hitting it. So typically that has to do with like how fast are the gas molecules going. Faster they're going, the harder they're going to hit that wall. All right, so that's what we're looking for gases. All right, we have actually lots of pressure units. All right, guys. And it just kind of depends on what you are using to measure the pressure as to which unit you're going to use. All right, so these, we have atmospheres. I'm going to underline them all for y'all over here. So we have atmospheres, which is ATM. I think atmospheres is probably the most common in science class, like the one that you'll see most often. But we do use all of them. I just think that one's the most common, probably. Then we have millimeters of mercury. Fun fact, or not fun fact, depending on how you look at it. We actually, in the US, instead of using millimeters of mercury, for most of our things, we use inches of mercury. So there you go, a little bit of customary versus metric for you right there. But yes, we actually measure in inches of mercury. Then we have Tor. It's actually named after a scientist whose name was, I believe, Torricelli. I'll have to check if my pronunciation's right there, but yes, named after scientist. And then we have pascals, kilopascals, and PSI. So like I said, whenever we're talking about weather, we measure in inches of mercury actually, but PSI is pounds per square inch. And you guys have definitely probably seen that one before. Because that is what you would use to like measure your tire pressure. So there you go, PSI. All right. So these are our different units, and they're actually written out down there as well. All right. And guys, up here, what we have is it's saying that 1 atmosphere is equal to 760 millimeters of mercury, is equal to 760 torr, is equal to 1.01325 times 10 to the 5th pascals, is equal to 101.325 kilopascals, is equal to 14.7 psi. Okay, guys. This is basically just telling us that these are all these are basically the same here. So this up here, this like list is what we could use as conversions if we need to convert from one type of pressure to another. And the only two that like typically need to be memorized, obviously you guys can use your notes because you're at home, but typically, just so you know for future reference, the only two that wouldn't be given to you is PSI because it's not, it's only really used in America, so it's not really something we would use very often. So PSI, and then the other one is pascals. The other 4 are typically on periodic tables and given to you, so you don't have to memorize those. But pascals and PSI typically are not given to you. But yes, since these are all equal, we can use them to convert from one unit of pressure to another. So that's what we're going to practice real quickly right here. So we are going to practice conversions, and I'm sure you guys have already guessed, but your best friend is back. A little bit of dimensional analysis. I know, so exciting. I'm sure you guys are all like just so pumped right now at home. We're going to start with this first one where it says convert a pressure of 1.55 atmospheres to kilopascals. All right, guys. So first step of dimensional analysis is always to take what's given. So my given here is 1.55 atmospheres. 1.55 atmospheres. Now then the question is atmospheres what I want? And if no, drop it low. All right, so we don't want atmospheres, we want kilopascals. So if no, drop it low. then we need a conversion. So that's where these numbers, again, up here are going to come into play. And based on those numbers, I know that 1 atmosphere is equal to 101.325 kPa, kilopascals. Okay, so that would mean since atmospheres is on top and on the bottom, atmospheres would cancel out, leaving us with just kilopascals, which is what we want. So now we can solve. And to solve, we multiply across the top, divide by the bottom. So plug it into your calculators. And just a quick reminder for you guys, when we're doing dimensional analysis, we do have to keep in mind sig figs. We're going to have to keep in mind sig figs this whole unit because we're doing math. All right, so but for dimensional analysis specifically, we look at our given. Our given has 3 sig figs, so our answer should have 3 sig figs. So I got 157 kilopascals kPa. Okay. Now for our next problem, it says, which is the higher pressure, 1.5 torr or 1.159 times 10 to the 4th pascals? Okay, so you guys could probably see these aren't in the same units, so we need to convert them to be in the same units. We really can't compare things that are in different units. It's just not going to work out very well for us. Okay, so I just personally am going to convert the pascals. Doesn't matter. I just chose it because it's a really big number. And I feel like it's easier to compare smaller numbers. So since we have 1.5 torr, I'm going to convert my pascals there just because, I don't know, I don't really like using scientific notation if I don't have to. So there you go. All right, so I have 1.159 times 10 to the 4th pascals. All right. And I want to convert to torr so that they're in the same units. So is pascals what I want? No, it is not. So I'm going to drop it low. And then again, I'm going to use my conversions from up there. So I have 1.01325 times 10 to the 5th pascals is equal to, then I want to get to torr, so that would be equal to 760 torr. All right, so that would mean that once again, since pascals is on top and on bottom, it would cancel out, leaving us in units of torr, which is what we want. So then we can solve. And again, I have 4 sig figs in my given, so I should have 4 sig figs in my answer. And I end up with 86.93 torr. So which one's the higher pressure? That one, because 86 is much higher than 1.45. All right. So pressure and temperature are definitely things that we're going to continue talking about throughout this unit. So make sure you do know how to convert to Kelvin and have a basic understanding of how to convert between pressures, because those are going to be used throughout and incorporated throughout the unit. So, but now what we're going to go ahead and move into is kind of reviewing some properties of gases and then talking about new properties of gases. All right, so first things first, all right, we're going to look at lots of laws that talk about the way gases behave, all right, and they typically are mostly, so there's actually like laws that basically tell us how gases are going to behave as we have changes in temperature, pressure, and volume. All right, we're going to talk about them, most of them by name, by equation, by word description, and applying it to problems. So I think you'll see what I'm talking about, but you should kind of have a general idea of what does this law say, all right? What's the equation for this law? And then how does this apply to us? All right, so first thing we're going to talk about, though, is just like behavior of gases. All right. So first thing we're going to do is I'm going to super briefly describe the 5 postulates of the kinetic molecular theory. Now, guys, we talked about, and I'm zooming super far in so that I can fit it all on the screen. Now, we talked about the kinetic molecular theory. It's been a while, but it was in our, why am I blanking out? IMF unit. It's where we talked about this. So you guys definitely had a video on the kinetic molecular theory. Pretty sure. Anyways, so we've talked about these a while ago, but there were 5 postulates. So I'm going to summarize them. So number 1 is that gases consist of particles. And the volume of those particles is negligible. All right, so so gases are made up of particles, and we might have said like tiny, very, very small particles. And guys, because they're so small, we can just basically say that their volume really is negligible. And it's basically because the particles are so small, and then compared to like the space in between the particles, that really their volume doesn't matter, doesn't really affect anything. All right, so that's postulate number 1. Number 2 is that our particles are in constant random motion. Which causes them to exert pressure. All right. Number 3, we say that our particles, when they do collide, they have elastic collisions. And what that means is that when they collide, they just bounce off each other and no energy is lost in our reaction. All right. Number 4 is that there is no attraction or repulsion between gas particles. So gas particles aren't attracted or repulsed by each other, just kind of neutral. And then number 5, our last postulate, is that we say that for gases, our kinetic energy is directly proportional to our Kelvin temperature. Okay, so those are our 5 postulates that basically say how ideal gases behave. All right, this is how we say gases should behave. These are the assumptions that we are making. However, guys, those are ideal gases, and we live in the real world. So there's kind of some differences between those. So real gases, number 1, they're slightly attracted. They have slight attraction and repulsion. It's not a lot, but they do. All right, so they have some attraction and repulsion. Number 2, our gas particles do have volume. They do take up space. And it does actually have, effects that make it so gases don't always behave the way they should. We can consider it negligible, but they do have volume. And then the third way that they are different is that collisions are not fully elastic. So collisions there is like loss of energy in those when collisions happen. Now then we can actually make our real gases behave more like ideal gases when we are at like really high temperatures. and low pressures. So they are going to behave more like ideal gases in high temperatures. That makes sense because the particles are going to move faster, which is going to, cause them to not feel those forces of attraction as much because they're moving pretty quickly. When they do collide, again, they're moving fast. They're not going to have those issues. And then again, at low pressures, gas particles aren't aren't squished together. So again, those collisions are going to be less frequent and they're not going to feel those attraction or repulsion because they're going to be farther apart. So high temperatures and low pressures. All right, guys. So on this next page, these are practice. All right. I want you guys to work these. All right. So, they are just conversions, pressure conversions. So I want you guys to practice converting your pressures here. And I'll give you the answers even. So the answer to this first one is 0.971. And the answer to the second one is 2.18. So there's the answers, but I want you guys to try them out and see if you can do them. Okay, so the next thing we're going to talk about is effusion and diffusion. All right, so the diagram over here shows us this one on the left. I'm going to write in colors because I want to, is effusion. And on the right, we have diffusion. All right. So basically, effusion occurs through a hole smaller than the mean path of moving particles. So what is the mean path of moving particles, right? What does that mean? Basically, the mean path is the average distance traveled by a gas molecule before it hits another gas molecule. All right, so how far can my gas travel before it hits another gas molecule? All right, so it's a hole smaller than the mean path of moving. So basically, I always think effusion is just gas escaping through a small hole. The way I always think about this is like getting a hole in your tire, something like that. Okay, and then diffusion occurs through a hole large enough to allow multiple particles to pass through at once. All right. Now, effusion typically transports particles more quickly because they're moving in the same direction, whereas diffusion, the particles could be moving both ways. Diffusion totally kind of depends on the concentration gradient. And then diffusion is limited by size and kinetic energy of the particles in the solution, as well as the concentration gradient, like I said. So things are always going to flow from a higher concentration to a lower concentration till they've evened out. Now, guys, different gases have different molecular masses, and so they travel at different speeds. All right. So what do you guys think is traveling faster, a heavy molecule or a lighter molecule? Okay, well, the lighter molecule is always going to travel faster than a heavy one. However, the kinetic energy of all gases at the same temperature is the same. So like velocity, how fast a particle is traveling, is not the same thing as kinetic energy. So like hydrogen, that's very light, is going to travel faster than oxygen, but they still have the same kinetic energy. So velocity and kinetic energy are not the same. Okay, so basically, kind of to sum it up, is effusion is gases escaping through a small hole, and diffusion is gases just traveling through like a much larger hole or area. I always think of like diffusion of like when you spray like air freshener in a room. It starts kind of in one area, but eventually it travels to the whole room. And then in this next little clip, I will show you guys how I think of effusion. If I'm good enough at iMovie to put it in, we'll see. So here's effusion. right, guys. So in our last section of videos, we are going to talk about relationships in gases. All right. So what happens when I change the temperature? What happens when I change the pressure? What happens to my gas? Okay. So the first law we're going to look at is Boyle's law. And Boyle's law relates pressure and volume. And I always remember this one, Boyle's law, by saying you boil peas and veggies. So Boyle's law relates pressure and volume, but you boil peas and veggies. You know, funny. Okay, so in Boyle's law, temperature remains constant, so we're not changing our temperature. And when temperature remains constant, pressure and volume vary inversely. So that means as pressure increases, volume decreases, or vice versa. So as volume increases, pressure is going to decrease. All right. Now then we're also going to show you guys, so that's the law. All right. We're also going to show you guys a quick graphical representation of this too. So I'm going to do Boyle's law right here. It's an inverse relationship. So basically what it would look like is that as my pressure decreases, my volume is going to increase. Or as my volume increases, my pressure will decrease as well. I guess that's the same thing, just backwards. I don't know. Anyways, so Boyle's law, you boil peas and veggies. Pressure and volume are inversely related. Next one is Charles's law. All right, and in Charles's law, it relates volume and temperature. So I always remember this one with Charlie on TV. So it relates volume and temperature. So in this one, pressure remains constant. And so when pressure is constant, temperature and volume vary directly. So that means as temperature goes up, volume also goes up proportionally, and vice versa. So as temperature goes down, volume goes down. All right, so let's draw Charles's law down here. So Charles's law, temperature and volume. As one goes up, the other goes up as well. That should be a straight line, but man, I'm bad at drawing. There you go. It's beautiful. Okay, the last law we have is Gay-Lussac's law. All right, and I always remember it as Gay-Lussac drives a PT Cruiser. So it relates pressure and temperature. And if you don't know what a PT Cruiser is, Google it. I think they are very ugly cars. So when volume stays constant, pressure and temperature vary directly. So that means as pressure goes up, temperature also goes up proportionally, and vice versa. So temperature, whoops, didn't mean to write in my highlighter. Pressure, again, very directly. This one is Gay-Lussac. So yeah, there you go, guys. Those are the relationships. And we will talk a little bit more about those in the next video, where Mr. Oglesby is going to go over the combined gas law, and we're actually going to get into more of the real math of this unit. Okay? Bye. Miss you guys a lot.